Buon pomeriggio, good afternoon to everybody. So thanks for being present at this new seminar. I recall that these are the seminar of the group of the UMI on Socio-Epidemiological Modellistic, and we're having a seminar every other week. And we have just arrived, so you can see on the site the schedule, the next three seminars that will be the next Friday. So they will be Cristiani, Shiguir 1, and Epidemicity the next. And then we will see what to do for the next year, but this will complete the program for this year. So thanks again. And so now it's our pleasure to introduce Marino Gatto. Marino Gatto is actually a graduate in engineering at Politecnico of Milano, but after a few years he moved from electronic engineering to ecology. So he's worked, I think, from around, even the end of 1970 on ecological problem. I remember he worked on forests and acid rains with the theoretical models on that. He has worked with biologists on the biology of many things. So for instance, I remember of eelfish and of other things, of more theoretical problems on life history. And then he worked also on problems in epidemiology. For instance, he worked, I think, on infection of fish. And then he has also did extensive work on cholera, especially modeling cholera in Haiti, interaction between hydrology and epidemic transmission. So a lot of interesting things. And like many scientists in the world, when the COVID epidemic made its emergence, he also worked on modeling COVID, and so has very extensive, has a very long list of publications. As he said, he has been a professor of ecology for many years. He was also the president of the Italian Society of Ecology, and so it's really a pleasure to introduce Marino Gatto. I think we first met in Stony Brook, probably, when he also visited Stony Brook for a week or so, and we met there. That was very long ago. And so
I'm not sure. I think that we met before. Or when you came back from Stony Brook. I'm not really sure.
Okay, but anyway,
but many years ago.
Many years. We worked on several things, but never really together.
Many years ago.
So okay. Please, Marino.
So let me thank Andrea for this very nice introduction. And okay, so good afternoon or good evening to all of you. And so let me start sharing my screen, which I will do. And then let me go to my PowerPoint presentation. And okay, now you should see my my whole screen now. So I'm going to introduce this topic with this little work that we have done on what we call epidemicity in recent years. And finally, I will actually present the work that we did on COVID-19 with the idea that the epidemicity index might be of some interest or might have been of some interest in some way controlling or preventing maybe what we call the second wave, at least in Italy, second wave of COVID. Now, well, what is the problem? And let me say that I'm really honored by seeing that Pauline van den Driesch is actually joining us. Because the problem is somehow related to so-called sub-threshold epidemics, and I think that Pauline and James Watmore introduced this term. Well, I'm not sure whether they were really the first who introduced the term sub-threshold epidemic in this paper. So what is the problem? Well, I think that all of you know the concept of the basic reproduction number, which, by the way, was derived from demography. It is nothing new for us ecologists, because nothing but the average number of daughter infections generated by one mother infection. So, and then, of course, it can be estimated in different ways, also depending on the model you adopt. You might adopt a compartmental model, as I will do, but you might use the integral differential equation, the integral equation, and so on and so on. So there are different ways of estimating or not. And then, of course, all of you know that if you have containment measure and changing the prevalence of susceptible and later times after an infection started, the average number of secondary infection per primary infection decreases, and you can calculate a so-called effective reproduction number. Now, if R naught is smaller than 1, or if RT drops because of containment measure and stays smaller than 1, well, we know that the disease will not become endemic in the long term. That's so-called herd immunity. However, epidemics are possible even if R naught or RT are smaller than 1. But in that case, what we call the epidemicity index is larger than 0. So I have summarized it in these two very simple graphs. So here we have R naught larger than 1. So you indeed have an epidemic at the very beginning. If by epidemic we mean the infection is increasing and somehow peaking. Sometimes it increases and does not peak, but anyway, the infection will persist, become endemic. Now here I am presenting a very simple case in which the endemism is a stable equilibrium, but then of course you might have more complicated situation with the attractors and or maybe chaotic attractors and so on and so on. Now, if R naught is more than 1, you might not have any epidemic at all, but there is a possibility that you have what I call subthreshold epidemic, and this term was introduced by I think I'm not sure, maybe Pauline can confirm that in that paper of if I remember 2008. So that's the subject and a way of my little talk today. Now, summary. First of all, I will make a little introduction, because the approach we take is an approach which goes back to the concept of reactivity and dynamical system, and the generalization of the concept of reactivity. Then I will talk about the application to epidemiological model, and in particular, I will introduce the epidemicity index. And then I will show that this idea of the epidemicity threshold is particularly important if you have inhomogeneities. And well, we've been very active actually in using spatial models of disease dynamics. And so Andrea has remembered that we've been working quite a bit with my colleagues, my colleague hydrologists, on cholera, and so I will present some results for spatial networks of cholera, where you have pathogen diffusion both via the water network, water transfer, and via the human mobility network. And then finally, I will present our work on COVID-19 epidemic in Italy, where, of course, the mainly the diffusion is via the human mobility network. Before going on, let me say that I want to remember all the people that have cooperated in different times and on different topics related to epidemicity, and Politecnico di Milano and Ecole Polytechnique and Università di Padova, like Andrea Rinaldo. And then Enrico Bertuzzo and Damiano Pazetto at Ca' Foscari. And I want to remember Ignacio Rodriguez Iturbe at Texas A&M, because with him we have Andrea Rinaldo and Ignacio and myself have written a recent book, which, by the way, I am showing here. Because the river networks ecological corridor has nothing to do with COVID. And in fact, the book appeared in 2020 before, well, let's say, or during the first phase of the COVID-19 epidemic. Okay, so that's the bibliography, our bibliography, but then of course there's a much larger bibliography on the subject. So let me start with the idea that is behind our epidemicity index. And that is the concept of reactivity. And Norbert and Causal, that the seminal paper which was published on ecology in 1997. And that's a very simple example in which you have a matrix A of a linear system, or more realistically, a nonlinear system, and yet you consider an equilibrium of that nonlinear system and new linearized and take the Jacobian. So these are two examples of Jacobians. And of course, they have the same eigenvalues, -1 and -2. So x equal to 0 is an asymptotically stable equilibrium. You start from the initial condition, and now you look at the norm of x. Of course, it will go to 0 in the very long time. But you see, with a matrix which is like A2, the transit behavior is different, and you can have a peak. So in this case, we say that the system, or the linearized system, is reactive. Now, so the first question is, how can you establish whether you have reactivity or not? And okay, that was established by Norbert and Causal in the same paper. And it's rather simple. So first of all, you define as reactivity the maximum rate of increase of the norm at the initial time. And then, of course, if there is at least one initial condition that provides a reactivity and increasing a positive reactivity, you say that the system is reactive. Because there's at least one condition. Then, of course, there are infinite conditions in a certain basin of reactivity. And the condition for that is quite simple, because you have to take the Hermitian part of A plus A transpose divided by 2, because, and then of course the Hermitian part is symmetric matrix, so the eigenvalues are real. So you take the leading eigenvalue, and if the leading eigenvalue is positive, then the system is reactive. So it's very simple. It's a very simple condition. Okay. Now you can generalize that concept, and that was a little contribution that came from our group, because in many problems, and typically epidemiological problems, you're not interested in the reactivity of all the state variables, but rather in the reactivity of subset or a linear combination of the variables. That's typical of, say, you have compartmental epidemiological models, or you have susceptible, infective, recovered, etc., etc. You're just interested in whether the infected or infectious are reactive. So it might have an epidemic. Okay. Now, so this concept actually applies to many ecological problems. So, for instance, we have started some very simple models where suppose you have a noxious alien species, so there is a resident species, then you have a noxious alien species, might be a competitor or a prey or a predator of the resident species. And you're not only interested in the fact that in the long run, these alien species cannot invade the environment, but there might be a transitory large increase of the noxious alien species, which is, of course, not commendable. And then, of course, if you go to epidemiology, so suppose you have a susceptible infected recover or a susceptible exposed infected recover model, and you are just interested in transient increase of the infected component. Or suppose that you have a waterborne disease, and so therefore you model the pathogen in the environment, that you might be interested in whether that pathogen, the pathogen reservoir is there's a transient increase, so there is an epidemic of that kind. So what is the condition for generalized reactivity? Now, what you consider some a vector of output variables, y, which you can describe through the output matrix C. Of course, you suppose that C is full rank, otherwise one of the other variables would be a linear combination of the other variables, so it would be useless. And then you ask whether the norm of y or can increase at time t equal to 0 for suitable initial conditions. And it turns out that it's very easy to generalize Norberg and Covenant condition, because you have now to take the Hermitian part of C transpose CA. So now you consider the leading eigenvalue of that matrix, and if the leading eigenvalue is larger than 0, then we say that the system is G-reactive, generalized reactive. And also it's easy to show that you can find the G-reactivity basis, so initial conditions that satisfy that quadratic inequality, they are in the G-reactivity basis. So this initial condition would give rise to an increasing norm of the output variables. Now, actually, you can do more, because, well, first, to take an epidemiological model, you don't want to know whether by perturbing the initial number of susceptible, there can be an epidemic. You are only interested in perturbing those state variables that will have some kind of effect on the output variables. So, for instance, on the infection. So you want to change the initial condition in terms of, say, putting a little bit of infection in the system, and whether that will actually provide an epidemic. Well, it turns out that that implies that you must consider the initial conditions that are in the complement of the kernel of C, and then you must consider now not the transfer of the matrix C, but the right pseudo inverse of the matrix C. And because the matrix C is full rank, then you can calculate the right pseudo inverse in that way by taking the inverse. Now there's some kind of advantage, because the dimension of the matrix C pseudo inverse is actually smaller than the dimension of C transpose CA. So you might think that calculating the leading eigenvalue is easier. On the other hand, you have to calculate an inverse. So I don't know whether it's really so important, but anyway, it can help. Now, so let me give you a simple example, because I want to point out that the generalized reactivity, of course, very much depends on the choice of the output variable. So even if you have the same system, depending on the choice of the output variables, you might have a system which is G-reactive or non-G-reactive. So we start from this very simple system with this matrix. This is really a very simple example with two eigenvalues. Okay, well, actually an eigenvalue with double multiplicity. And you see that if you choose the matrix, which is the identity matrix, in that case, you go back to the reactivity of numbers and counters, and the system is not reactive. So the normalized norm of the output is decreasing. But then, for instance, if you give weight only to variable x1, okay, now it's clear that for variable x1, so the choice of matrix C3, then you might have an increase of that for, for proper initial condition. So for proper initial, for instance, if you take this initial condition, then x1 will first increase, and then of course it will go to 0, because anyway the two eigenvalues are -1. And instead, if you consider only the variable x2, now the variable x2 is anyway decreasing, so there is no reactivity. And then, of course, so for instance, if you give more weight to variable x1 and less weight to variable x2, sorry, then you might have reactivity. Now, okay, that should be clear. So the concept of G reactivity is very much dependent on the choice of the output variable. But that, in a way, you make everything more flexible, because in a way you might have, say, a political choice where you decide that that kind of variable is the most important. So, for instance, if you take a spatial model, you might say, well, I don't care whether maybe the infectious people are increasing in one place. I just consider the total number of individuals that are infected, for instance. Okay, so you can make different choices of your output variable. Now let me go specifically to epidemiological models, because in epidemiological model, we typically consider the disease-free equilibrium. So we linearize around the disease-free equilibrium. So the matrix A in that case is the Jacobian at the disease-free equilibrium, and Y is typically either the vector of the states at infection, with the same meaning of, for instance, famous paper of Dickman in 2010 on the next generation matrices. Or more generally, you might take a linear combination of state and infection. So you might have exposed, you might have infectious, you might have pre-symptomatic, and so on and so on. It might give different weights to those compartments. So the stability of the disease-free equilibrium is related to the leading eigenvalue, or the more, I know that Stefan Mikkel is now connected. He likes to say the spectral abscissa, is that correct? The spectral abscissa of A. The epidemicity, the reactivity, is actually related to the leading eigenvalue of the Hermitian part of CAC pseudo inverse. That we call the epidemicity index now. So from now on, I will talk about epidemicity index. So the epidemicity index, in that case, is take the disease-free equilibrium, take the Jacobian at the disease-free equilibrium, choose the output variables that are related to the states at infection, and then you build the epidemicity index, and you take the leading eigenvalue of the Hermitian part of C pseudo inverse. Now, can you relate all these to the reproduction number? Well, you know, there are a very special case. Suppose now that Y, the output variable, is the vector of the states of infection. So you consider all the states of infection. So for instance, in a susceptible, exposed, infected, recovered model, you consider the exposed and the infected. Now you can use the approach of the next generation matrix, okay, which was pioneered by Dickman, Aston, their 1990 papers. But then in a way, the most recent paper of 2010 explains clearly how to do that with very many models. So in this case, the dynamics of the vector of the states of infection given by that equation, in which the Jacobian can be actually considered the sum of two matrices. One sigma is the transition matrix. So it is the matrix that contains the rates at which you go from one state of infection to another state of infection. So the inverse of the residence time in each state of infection. And then the remaining part is the transmission matrix. So you can build the basic reconstruction number, as Dickman et al. Pointed out, at the spectral radius of minus the sigma to the -1. Okay. Now, of course, now in this case, the matrix C is the identity matrix. So the epidemicity index is the related to the emission part of T plus sigma. Sorry, I wrote something wrong. I didn't mean it's not the emission part. It's the leading angle value of the emission part. And so when we talk about subthreshold epidemic, we mean the case in which the spectral radius of minus T sigma to -1 is more than 1. However, the leading eigenvalue of the emission part of the Jacobian T plus sigma is larger than 0. Okay. Now, up to now, this is supported by, let's say, theorem and proofs. When we go to the so-called effective reproduction number and effective epidemicity index, that is kind of heuristic. Of course, if you have containment measure, and these containment measure are varying in time, and the prevalence of susceptible is decreasing because of the containment measure or the vaccination or whatever. Or it might be increasing because the immunity is lost, and so on and so on. So actually, those two matrices, T and sigma, might vary in time. So you take the spectral radius of minus T sigma T to the -1, and then you calculate that maybe with moving a window, suitable filtering, and so on and so on, and then you call that the effective reproduction number. And in the same way, you can now take the emission part of T plus sigma T, take the leading eigenvalue of that emission part, and call that effective epidemicity index. Now, so let me start with the two case studies. And the first case study is cholera. Cholera been studied by our group very much. By our group, I mean our group at the Politecnico, the École Polytechnique de Lausanne, University of Padua, the University of Venice, and also Ignacio Rodriguez Iturbe, first at Princeton and then in Texas A&M. You know, anytime I speak of cholera, I want to remember this great Italian, Filippo Pacini, who nobody remembers, at least in Italy, because in 1854, well before Robert Koch, he discovered not only that the cholera is due to infected water, but he discovered the pathogen, the bacterium, Vibrio cholera. Okay. Now there are different serotypes, but mainly only a few. Practice 01 and 139 that are pathogenic to humans. Transmission is oral fecal, but basically via the ingestion of contaminated water or food. And usually the inoculum is rather high. You need about 1 million bacteria for starting the disease. The main reservoir is water, so you can find Vibrio cholera everywhere, and it's a normal component of ecosystem, especially in, say, Laguna or near the coast. The incubation hour is quite variable, 2 hours and 5 days. One very important thing that somehow relates cholera to COVID is that a lot of infectious people are asymptomatic, but they produce bacteria, their fecal excretion, for a few days. With asymptomatics, only few develop acute symptoms with watery diarrhea, dehydration. Of course, if they are not rehydrated, they will die quite quickly. Recovery time is about 5 days, and the immunity, well, there is a acquired temporary immunity. It's not clear how much it lasts, can depend very much on each individual. Now, the basic eco-epidemiological models, well, the very first one was due to Vincenzo Capasso and Stefano Pava in Fontana, 1979, because unfortunately they experienced one epidemic of cholera back in the 70s. I was actually vaccinated against cholera during my military service. But the model to which make reference is one by Claudia Codesso, and it has now susceptibles, infected and infectious, bacteria in aquatic habitat, and then of course you have recovered that are immune for a certain time, and then they might lose immunity. But in the model I'm going to present, we do not consider that at least in the short term. And with the simple model of Claudia Codesso, you have a model of that kind. And okay, here it's susceptible, infected, and time. But the most interesting thing is when you consider a spatial model. And no, I want to show just the result of this spatial model that we developed as the big cholera epidemic in Haiti. Oh, I'm sorry. So just to give you an idea about the data, it started in a certain, along the Artibonite River, and then it was spreading everywhere. And so we developed a spatial model. And to that spatial model, now referring to see how the epidemicity index might be useful. So the spatial model now at many locations, and you have susceptible, infected, and bacteria in each location. For simplicity, at least in this model, we assume that we have two networks, the hydrological networks and the human mobility network, but the nodes are common. Of course, you might have more complicated model with a multiplex network where the node of the hydrological network and the node of human mobility network do not coincide. But somehow you can manage that and do them coincide. If they coincide, then you can introduce the different ingredients. So the first ingredient is the dose-dependent infection rate. So you can consider that the force of infection is actually saturating with the concentration of bacteria in the water. Then you have a certain percentage of the individuals that are mobile and others that are not mobile. And then you have two important matrices. So the matrix PIJ, which is the hydrological connection matrix, and QIJ, which is the human mobility matrix. And these describe the, let's say, the probability with which pathogens are moving along the hydrological network from node I to node J, or the probability with which humans are moving along the mobility network from node I to node J. And then, okay, you can introduce, of course, the hospitalization rate for the people that are infected, and of course, if they are hospitalized, we suppose they are no longer infectious. And then you have the contamination rate. So people are defecating in a certain volume of water. The infectious, of course, are producing pathogen, and they are increasing the bacterial concentration. And then, of course, you have the fact that pathogens are taken from one node of the hydrological network to the other node of the other network through the flow of water. Okay, so the case I'm presenting is a case where we do not consider now a real network like in the Haiti case, but we are considering what we call optimal channel network. These are artificial networks that, however, have the same topological property of real networks. So you can mimic a real hydrological network, and also you can mimic the flows along the hydrological network. And you see here different possibilities with the outlet at the center, outlet or the outlet in the core, and so on. In terms of the mobility, you can use what we call the gravity model. So in the gravity model, the flows between nodes is proportional to the population in each node. And then you have an exponential kernel. So with the distance, of course, the flow will actually become smaller. Of course, matrix Q is rho stochastic. And then let me go directly to the results. So here we have considered output variables. What? Well, here you have the infectious people and the bacteria. Now, bacteria are normalized with respect to the semi-saturation constant in that force of infection model. And then you see that you have the weights. You might weight more the infectious people, you might weight more the bacteria. So in this way, you are considering as output variable both the increase of infectious people and the increase in the nodes and the human communities, and the increase of bacteria, again in the nodes that are in a way the reservoir of the hydrological network. Now, here is the results. Suppose that you consider different exposure rates and different contamination rates. Okay, so if you have a very large exposure rates and very high contamination rates, you have an unstable disease-free equilibrium. And actually, this is the boundary along which R naught, the reproduction number, is equal to 1. However, you might have regions of the parameter space, typically this one or this one, where R naught is smaller than 1, but the epidemicity index is larger than 1. As larger, sorry, than 0. So you have a G-reactive system. So, and then only if you take a very low exposure rate and very low contamination rate, you have both R naught smaller than 1 and the epidemicity index, which is negative. Okay. So you might have a situation like this one, that is typically a system which is G-reactive, but with R naught smaller than 1. So this typical sub-threshold epidemic. Or if you are in this region of the parameter space, you do not have any reactivity. Now, if you change, the weights, Ci and Cb, then of course that frontier, that boundary that divides the parameters that will provide you a non-reactive or a reactive system can change, but you see basically the shape is the same. So that results. So you see that at least for cholera, you might have this situation. Now, suppose that you implement containment measures, so you're decreasing both the contamination rate and the exposure rates, because you provide good drinking water and you provide sewage. So you're taking beta and theta down. How much? Well, the usual problem would say, well, take that down so that R naught is more than 1. Well, according to our idea, that will not prevent at least some temporary epidemic. So better if you go to a non-G reactive and stable disease-free equilibrium. COVID-19 in Italy. For COVID-19 in Italy, we developed a spatial model. Okay, this is the result of the spatial model that we developed back in April 2020, with and you see the data in the so-called first wave. So everything started, if you remember, in mid-February, and here you see the data up to the end of March. And we developed a model at the scale of the province, and you see the data on the right and the simulation with the optimal, with calibrated model in the middle for the provinces, and then a fancy reconstruction of municipalities on the left. So that model is again a compartment model. It is spatially explicit, and it considers susceptible. It considers exposed. So these are infected, but they are not yet infectious. And then when we consider the infectious people, they are divided into three classes. What we call the pre-symptomatic, so people that are infectious, and actually they are very infectious. The pre-symptomatic people are the most infectious, and with the, let's say, not the present variant, but the variant, the genotype at that time, it got about 5 days. The peak of infection, and you are not symptomatic, but then you might become really symptomatic or mildly symptomatic or even asymptomatic. And then, of course, we have hospitalized, quarantined people that are isolated, and disease then recovers. And then you have the mobility metrics in different, okay. And that describes the movement between provinces. Okay. So here you see the equation. The force of infection is, of course, complicated because the force of exchange takes into account susceptible people moving from, let's say, a node I going to a node J, meeting an infected guy in J, or an infected guy and J moving to I and meeting a susceptible guy and infecting that. Or two people, one susceptible, one infected, one in I and one in J, and they go to work in K, and then the infectious guy will actually infect the susceptible. So that force of infection is in a way the core of our model. We have transmission rates that are different for pre-symptomatic, infectious but asymptomatic, and infectious and symptomatic. And they are different. And actually, from calibration, it turned out that confirms there are other data that the transmission rates of the pre-symptomatic is quite high. Okay, oh, I'm sorry. And then we explore the scenarios after the release of lockdown. The release of lockdown started at the beginning of May 2020. And here you can see the result and the title of the paper discussed that. So of course, now the betas were decreasing, and also the mobility of people was decreasing because of the lockdown. And so we calibrated the model up to the end of May, and we made scenarios up to the release of the lockdown, supposing that the blue line is the baseline scenario. Everything is going on as if the lockdown were still going on, with people anyway taking care, or green and purple solid lines show instead what might have happened with the transmission rates going up 20% or 40%. And at least all the Italians know that actually things were going well up to, let's say, mid-July. And then the curve gradually increased. And so we had the second wave. So the question that we asked, can we apply our epidemicity index to the Italian case? And what does the epidemicity index say? So what we did, we applied what I showed to you. And so we calculated the basic reproduction number, the effective reproduction number, and then the basic epidemicity index and the effective epidemicity index. Now, let me show to you, first of all, the situation. Okay. So we want to know whether you have a situation like that with reference to a toy community. So consider now that model, but you have just two nodes, just to make everything more clear. So first of all, you can play with that model, all those compartments, with just two nodes. And community one is twice as large as two, but people of community one are less mobile than those of community two. So for instance, Milano and Piacenza. Milano is attracting many people, and not many people living in Milano are going to Piacenza, but many people in Piacenza will come to Milano. And here you have now a different parameter space. You have the local basic reproduction number. So suppose that Milano is completely isolated or Piacenza is completely isolated. And then we can calculate the reproduction, the basic reproduction number there, R01 and R02. Okay. Now let's instead mobility act, and we now calculate the reproduction number with mobility and the effective and the basic epidemicity index with mobility. And here is the situation. So here you have the frontier are not equal to 1. Here you have the frontier epidemicity index equal to 0. So you see that all the gray area is where you have a stable disease-free equilibrium, but the system is reactive. So even if you take down the local basic reproduction number, which means that, for instance, you implement block of mobility and so on, that might not be enough. And now let me go to the real case, the real Italian case, because we estimated the effect of the containment measure. And as you know, containment measure can be of different kinds. You might have personal protection equipment, masks, barriers, etc., or physical distancing. You might have decreased mobility, so you block mobility, as put down in Italy with the lockdown. You might test people intensively and quarantine people, or you might combine. So how can you evaluate effectiveness? You can do that. First of all, you might suppose that you apply the containment measure from the very beginning. So you can calculate the reproduction number with containment measure at the very beginning when you have really a disease-free equilibrium with the prevalence of susceptible equal to 1. And you can do the same with the epidemicity index. Then you can go to a sort of heuristic part where you calculate the effective reproduction number and the effective epidemicity index. So let me first show the effect of containment measuring in terms of the reproduction number and the epidemicity index as if they were applied at the very beginning. And here you see the results. Now, the reproduction number of Italy was close to 3, and that is more or less the same everywhere, almost everywhere. And here you see the effect, for instance, of personal protection equipment with reduction of transmission. And first of all, suppose that you apply one single containment measure. So to achieve a reproduction number which is more than 1, you should have reduced the transmission in Italy by about 60%. But that would not have been sufficient to bring the epidemicity index to being negative. In that case, you would need a reduction of 80%. What is the effect of travel restriction? Well, travel restriction, if applied, that only that can never bring the reproduction number below 1 and the epidemicity index below 0. However, you can see that there is a certain difference, that in a way, the decrease of the epidemicity index is, let's say, more sensitive to travel restriction than the reproduction number. Okay. What about isolation rate? Again, the isolation rate, that is rate in terms of days to the -1, people quarantine per day. And you see that it is very efficient in a way in terms of reducing the reproduction number. Also, if you think quarantine 20% of the infectious people every day is not an easy task, it is not so effective in terms of reducing the epidemicity index. And then, of course, you can combine. And here you have okay, what you do, suppose that you have different reduction of mobility, and then you might have different transmission reduction, different isolation rate. So let me show, first of all, some simulation that we did. Okay, suppose that you see 100 infections in each province, and you look at what? Suppose that mobility is down to 50%, and then you can isolate 10% of the infectious people every day. And then you consider 3 different values of transmission reduction: 50%, 33%, 26%. So you isolate or you quarantine half of the infectious individual, 1/3 and 1/4. And you see the different results. So if you isolate only 26%, you will have a reactive, okay, reactive. And I'm sorry. And here you see a map of Italy. So you see that, of course, depending on the initial condition, on where you see the 100 initial infection, you might have different results in terms of total infection in Italy in the next 90 days. So you see that, I'm sorry, when I'm moving my mouse, then I to show to you the maps, and then sometimes the slide go to the back slide or the next slide. And you see that in a way, the infection seated in the southern province would have been more important and more reactive in a way. Another thing that you can do is to seed 100 infection in the 10 busiest airports. And here you see the results of the number of the number of infections in each province. And then, of course, you can see that obviously the infection will mainly increase near the airports, Milano, Rome, Naples, Palermo, and so on. The final result now that we can evaluate the effect of containment measure, not only for those cases that I showed, but let's suppose that the mobility is down to 50%, and now you can see different transmission reduction and different isolation rate. And so, okay. And so you see that here you have herd immunity and no epidemicity, when there is a very high transmission reduction, very high isolation rate, together with mobility down to 50%. Here, you instead have a subthreshold epidemic, So herd immunity alone, but epidemicity index, which is positive. And of course, here you have no herd immunity with the reproduction number calculated as the disease-free equilibrium, which is larger than 1. And then, of course, you can calculate for different values in the gray region the total infection. So depending on the shade of gray, you might have different. And of course, the more you go towards no herd immunity, and the larger the number of the medium of the total infection. So you see that, however, a very big result that proves that vaccines are very useful is that if you want to have both herd immunity and no epidemicity, that implies, let me say, heroic efforts. So mobility down to 50%, transmission down to 50%, isolating 50% of the infected people per day. You know, that's really big effort. Now, the final is about the effective epidemicity index. How was the effective reproduction number and the effective epidemicity index during summer 2020? Well, you see that why the effective reproduction number was below 1 and the lockdown was very effective. During summer, and well, let's say, in any case, the epidemicity index was positive. So even during summer, and you may remember that in fact, at least the Italians, maybe not Pauline, may remember that there were continuous flare-ups of infections in Veneto, and one maybe near Rome, and one near Naples. So our idea is that if you do not prevent epidemicity, that you might have these continuous flare-ups, and these continuous flare-ups, if you consider now a spatial model, might coalesce into what was the second wave of Italian infection. So, final conclusion. We believe that defining this epidemicity index, you can establish the occurrence of sub-threshold outbreaks, Sensu, Vandendrich, and Watman. Now, of course, an open issue is the operational definition of the geographical boundary we've been considering in Italy, but now COVID is everywhere in the world. So, of course, now no epidemic may be in Italy, although there are some signals that are not very comforting, let's say. But everywhere in the world, the situation is different. So you might have a multi-scale approach, for instance, like the one that is used for climate models. And then, of course, that our last slide, in a way, suggests that if you calculate effective epidemicity index and if you see that they are positive, that might be a warning signal for adopting precautious measures to avoid the coalescence of epidemic flare-ups and then second or third waves of infection. Okay, I stop here, being too long. I know that, and then I'm sorry, and I hope anyway you enjoyed my presentation. So if there are any questions, I'm ready.
Okay, thanks, Marina. It was nice. We're not sorry for being long. So there is time for some questions. You can. I think you can just raise your hand, or even since there are not so many, just unmute your microphone and ask a question if you wish.
So I stop sharing, maybe.
Yes, okay, maybe I ask a question while we wait for other. So with the epidemicity index, you're saying that some combination of the parameters of the infective in the different place can increase depending on, but somehow to have a real coalescence, then you really need at some point that somehow that the increase put them together. So it's
yes. I mean, you're quite right. So we have no real result about the occurrence of coalescence. So that's just an intuition. Of course, we try to simulate in a way the coalescence by supposing that, for instance, suppose that you have random foci of infections. And so I think that Lorenzo Mari is connected. So he did some simulation, and with random foci of infection of different types in different parts of Italy. And if the epidemicity index is positive, you can have that sort of coalescence. Well, I think that in a way, the second wave of infection might have been a coalescence. But okay, it's not proved. It's just a sort of intuition. Lorenzo, do you want to say anything?
Hi. No, I think you're quite right. I mean, we tried to do some simulations, definitely, but we didn't have too much time to go into that direction. So that's something that definitely needs to be studied more, I think.
Okay, thank you. Other questions or comments?
Marino, I just thank you for your talk, very nice talk. I just wondering about numerical schemes that you adopted, and in particular, if there is an equivalence for a numerical method to be reactive or not. I mean, as for stability, we require that a numerical method, for example, for high stability, has the same behavior as for the continuous model. Now, there is some research in numerical field in order to investigate about the reactivity feature of reactivity characteristic of numerical scheme when you apply this numerical scheme in order to reproduce, to make your simulation?
Well, you know, I'm not an expert of numerical methods, but my colleagues, co-authors, they are, and I believe that they applied the correct numerical methods to, of course, it requires numerical methods of course, to find, for instance, the eigenvalues and so on, but that's not a big problem. It requires numerical method to simulate the equations. But the biggest computational effort is, of course, the calibration of the model, because so there's always a trade-off between a model being not too parsimonious, if you want the model to be realistic, but not with very many parameters, otherwise you cannot identify the model. So we've been using Bayesian approach mainly. Of course, with the prior of the parameters that were actually taken from the available literature. So there's a lot of literature, for instance, on cohort analysis of infected people to see how much they will become infectious and so on and so on. So, okay. Other, of course, the mobility metrics, again, was taken from data that came from the statistical. They were not updated. We updated them with data on mobile phone. and so on and so on. So I would say that the most important, the most difficult part in terms of numerical analysis, the calibration, really. I don't think that there are so many problems in terms of the simulation of the differential equations. Also because after all, it's 107 provinces. And that we consider that at the reasonable spatial scale, also because the data were not available at a very fine spatial scale. And on the other hand, going to a very fine spatial scale would have increased the number of equations, the number of parameters, and so on and so on. I'm not sure that I answered your questions.
No, it was just a curiosity if there is some reactivity that can be only induced by the numerical method, but that
no. You mean that?
That's my
No. I think that we were careful enough not to that kind of result. But you are quite right.
Okay.
No. Yes.
Related on this subject.
No. That's right. And in fact, you might have, for instance, when you have, say, oscillating system, and then you might observe oscillation. And these oscillations are not really that due to the numerical method. No, that was not our case. No. Okay.
Thank you.
You're welcome.
Okay. Other questions? Well, if nothing, I think it was a very interesting seminar. So I thank all the participants and especially Marino, of course. And I hope to see you in 2 weeks, November 10th. That will be next seminar.
Well, thank you, Andrea, and thank you all for the attention. Sorry for being so long. Sometimes I am transported by my enthusiasm.
Ok,
Goodbye.
a tutti.
Ciao.
Arrivederci.
Ci vediamo.
Thanks.
Ciao, grazie. Ciao a tutti.
Ciao.
Ciao.
Ciao a tutti, grazie. Ciao.
Arrivederci.
Arrivederci. Ciao.